This video demonstrates the integration of the Wuppertal Pilot Application into the Sudplan scenario management system. It is divided into 7 parts, whereas the first 3 are of preparatory nature and the latter 4 depict the main workflow. Part 1 shows the import of a new local model configuration. In Part 2, a new monitor station is added as a preparation for Part 3, where we will see how an IDF curve is imported into the SMS. Part 4 then deals with the generation of rain events from IDF curves. After all these steps, we move on to Part 5, where an initial model run is done and the results are investigated in 2D, 3D and 4D. In Part 6 we actually see how to manipulate the initial model, run it again, and eventually see the impact of the changes. Finally, Part 7 shows how climate information comes into play and how they influence the local model results. In order to be able to actually do planning, we need an initial local model configuration. The local model configuration, in fact, consists of 2 rather independent configurations for the 2 models that are involved in the calculation: GeoCPM and DYNA. GeoCPM is able to calculate the flow of the water on the surface, and thus its configuration contains, amongst other measures, a TIN, which means Triangular Irregular Network. This is the data that can later on be manipulated to support our planning process. DYNA, on the contrary, is responsible for flow calculations within the sewer system. In the context of this pilot, this data is static because currently it does not support changes of sewage drains yet. However, as only a combined calculation is really accurate, we need it too. So to actually import a new local model configuration, we can use the Import GeoCPM configuration wizard. First we choose the GeoCPM configuration file, geocpm.ein, either by entering the path directly or by browsing to its location. After that we have to provide the DYNA configuration folder, which is the folder where all the relevant DYNA files reside. In the next step we are asked for some metadata such as the name of the configuration, an optional description, and an investigation area, which has already been created in our case. The next step now processes and uploads the configuration data so that in the end a new local model configuration is created. This process has been shortened for this video, as it can take several minutes or even hours in case of a very complex configuration. After the wizard tells us that the import was successful, we can close it. Browse to our new configuration. And view the results of the import. On the left of the description pane, we see the global settings section of the configuration, which is not editable for us. And on the right is a map preview. We can double-click the preview and the mapping component shows us the actual imported data. The blue lines represent building break lines, whereas the red ones are boardwalk break lines. Additionally, if we zoom in far enough, we, too, see the actual TIN, which might come in handy especially for modeling experts, for example, to detect modeling errors. By the way, right now we see a part of the Schloss Lündenbeck, or Lündenbeck Manor House, that constitutes the critical infrastructure in this area and which we later may want to save from extensive flooding. But to find out if this building is really endangered, we have to run the model first. After a successful import of the configuration, we need a rain event to apply to the model. Currently the SMS supports generation of rain events from IDF curves. However, proper IDF data has to be imported first, and imports of rainfall data is not possible without a monitor station which tells us where the rainfall data originates from. Thus we first of all use the map to navigate to the area where our monitor station is located. As we want to import IDF data, we only need a virtual location because IDF data is statistical rainfall data valid for a certain area. So we select the new point mode from the toolbar of the mapping component and click somewhere in the area of the manor house, because our IDF data that we want to import later on is valid here. After that, we open the Objects widget and see that there is a new point in the list. This is our point that we just created. If we select it, the point on the map is also highlighted so that we know which one we just selected in case we created more than one point. We give our point a new name in order to recognize it later on. Now we explore the rainfall data in the catalog and find a node called Monitor Stations. We can do a right click on the Monitor Station node and find an action called New Object, Monitor Station, which we now use to create a new station. The Monitor Station editor appears and we can give it a name. We have to choose a context, in this case rainfall, as we want to associate rainfall data, and we can choose variables that this station is able to monitor. Finally, we choose a geometry. The geometry combo box offers us our demo monitor station point, which we previously created. We select it and save our entries. If we explore the monitor station node now, we find our newly created monitor station. We can have a look at its description or can visualize it on the map too. Now we are ready to import our rain data. As we want the most accurate results for our runoff simulation, we need our own data in the SMS. So we import an IDF curve that contains data valid for our area of interest. To do so, we can use the IDF curve import wizard that can be accessed from the SMS main toolbar. At first, we are asked to provide a file that contains our data. We browse the file system and select the file to import. In the next step, we have to choose an appropriate converter so that the importer is able to transform the data of the selected file into the internal format of the SMS. In this case, we need converter number 2. Step number 3 does the actual conversion of the data. As soon as it is finished, we reach the final import step. The IDF curve needs some metadata like a name and a monitor station. We choose the monitor station we just created before. Finally, we enter a year representing the statistical IDF data and finish the wizard. Now we see our IDF curve in the IDF curve tree of the catalog and can have a look at its values. We are nearly ready to do an initial runoff simulation. However, the runoff model cannot deal with IDF data, but with single rain events. Fortunately, the SMS supports generation of Euler rain events from IDF data. We simply have to select the desired range for the rain event and use the Euler rain event generator wizard that is available from the contextual menu of our selection. The generator can use the selected data to either generate an Euler 1 or Euler 2 event. As the Euler 2 event is more appropriate for our simulation, we choose it. In the next step, we are asked for metadata such as a name and a description, which is optional. Finally, the event is generated. This usually is finished in a split second. Eventually, we can leave the wizard and find our new rain event in the rain event tree and can have a look at its values. After we imported our initial model configuration and created an appropriate rain event, we are all set to start an initial simulation. To do so, we can select the initial local model configuration and open the description pane, where we find the simulation action in the upper right corner. It opens the simulation wizard, which lets us select a model configuration. It is already pre-selected and we can go on. After that, we have to choose a rain event, and we use the one we previously created, of course. Finally, we enter a name for the run and instruct the model to run by finishing the wizard. This simulation will take several hours, so we have a look at the run that has already been done before with the very same data. When a simulation is initiated, a new scenario is created and appears in a scenario node of the corresponding investigation area. It shows information about the status of the simulation and links the input, and as soon as the simulation is finished, the output too. The output shows some statistical data about the results and additionally a preview on the map. We can double-click the preview and are presented the actual results as a layer in the mapping component. The layer represents the maximal water levels per cell of the tin. We zoom to our area of interest, the Lindenbeck Manor House, and we can see that the model calculated that if this rain event would have happened, the flooding and thus the damage to the manor house would have been substantial. Normally this kind of result presentation is sufficient for urban planners to introduce some countermeasures. However, especially for affected citizens and city managers or politicians, a visualization of the result in 3D or even 4D is more suitable, as it will appear more natural to them. So we can take the results and drop them in the SMS integrated 3D component. We can choose between the maximal water level visualization, as in 2D, and the water flow visualization, which is actually 4D. At first, let's have a look at the maximal water levels. As the maximal water level result visualization is provided as a WMS layer, the 3D component asks which type of layer we want to add. We have a choice between a so-called texture layer and a so-called height layer. The texture layer type leads the 3D component to directly map the layer information to the surface. The height layer allows to visualize the layer data as a plane on a certain height above sea level, which can be changed individually. Here we choose the texture layer visualization. We can see that the results now look like in 2D, but with the difference that we can see the topography of the area. In order to gain a more realistic impression of the area, we add some building data. Now the visualization gives us an even better understanding of the urban planning context. But we might want to have a look at the curse of the water too. So we drop the results on the 3D component again, but this time we choose the chronological sequence of water levels. Now it takes a while until the results are visualized, as this is a rather huge amount of data that we loaded and processed. Eventually we have a visualization that cycles through the time steps of the simulation time span and visualizes the specific water levels. Now we get an overview of the situation, and we have to do countermeasures to minimize damage in case of such an event. To support the urban planner in reducing the effects of stormwater events on critical infrastructure, the SMS offers ways to manipulate our local model configuration that we previously imported and that we use to gain insight in the current flooding situation in case of a heavy rain event. At the example of the Lundenbeck Manor House, we will now play through a possible planning option to prevent damage by water. We will use the possibilities of the SMS to create two retention basins connected by a graben so that water can be exchanged. Additionally, we add a wall at the back and front side of the manor house to prevent the water from slopping over the borders of the retention basins. Eventually, we will run this newly created configuration and we will see if we succeeded. We start with the display of our initial configuration. Additionally, we display the results of the initial simulation to get the general idea of the critical spots. Now we navigate to our area of interest, the Lundenbeck Manor House. The basins will be created on the back and front side of the manor house at the very area where the water already concentrates. To do so, we zoom in to get a better view of the situation. Select the new polygon feature and draw a polygon that depicts the extent of our new retention basin. After that, we select the Select tool, do a right click on the new polygon to open the contextual menu and use the Manipulate Surface action. A Wizard Preparation dialog pops up and does some checks for the area the polygon spans. When it is finished, the wizard will start, or as in our case, a conflict dialog pops up. During the preparation, our editing area is searched for breaking edges that intersect with our polygon. This is done because it is forbidden to manipulate the points that are used for the definition of breaking edges, and if such a conflict had been found, we would not be able to actually start the wizard. In our case, there are manipulated surfaces that intersect with our new polygon, and it is not allowed that a point is affected by two different manipulations within the same configuration. So the dialog allows us to start the wizard, but with the restriction that configurations already covering points within the area of our polygon cannot be used for the manipulation. As we wanted to create a new configuration anyway, we don't have to care about this warning. The dialog also offers to show the conflicts that were found on the map, and then the conflicting objects will be blended in, but we want to start the wizard right away. The first step is to decide about the new height and the type of the surface manipulation. There are two different types of manipulation. A manipulation relative to the current height and an alteration absolute to sea level. The former means that every point of the tin that lies within the area of our polygon is lifted or dropped according to the height that is entered. That way, all the points will keep their relative position to each other, and the topography within the area is not changed at all. The latter denotes an absolute change of all covered points to the given height above sea level. So a basin with a plane base is created. In our case we want the latter, so we choose the desired height and select absolute to sea level. After that we can add metadata to the manipulated surface, such as the name and an optional description. In the next step we are asked to select the configuration to which this manipulated surface shall be added to. There is no configuration but the initial one, and as soon as we have selected it, the wizard hints us that a new configuration will be created. It is to say that the initially imported configuration will never be changed. The SMS only stores the delta between the initial configuration and the modifications done with the SMS. This saves storage space and ensures that the initial configuration will remain untouched. After a click on Next, we can configure our new configuration by entering at least a name. Finally, the Finish button takes over our changes and saves the new configuration and the new manipulated surface. We find the configuration in the catalog below the calculation model node of our investigation area, and the new polygon feature has turned into a manipulated surface that is visualized on the map. Now we need a second retention basin on the front side of the manor house, so we repeat all the steps that we've just done to create the first retention basin. We go to the right spot create a polygon, open the wizard, enter a height and a type, enter a name, select our previously created configuration and finish the wizard. Now we have two retention basins, but we also want to connect them and create additional walls to prevent the water from slopping over. This is an easy task, as the creators of the initial configuration already created some null breaking edges that we can manipulate. Breaking edges are structures that are kind of a cut in the terrain from the model point of view. That way we are able to create and manipulate vertical structures where the creators of the tin foresaw it for us planners. During the initial import of the configuration data, all those structures have been processed and are now visualized by the so-called breaking edge layer. Moreover, all of them are stored as individual objects so that they can now be found and manipulated. Hence, to create our connection between the basins and the walls, we can use the already present breaklines. We choose the breakline class from the Spatial Search button menu and choose a line for a search geometry. With a little skill, we can draw a line that intersects all the breaklines we want to work with for our scenario. This is how the Spatial Search works. It searches for all objects of the types that were selected, whose geometries intersect with the drawn search geometry. Thus, we see the search results. 4 breaklines. To get a better idea which one lies where, we add them all to the map. The added objects are now visualized in the map, and we can select them either in the search results tree or in the objects view to see where exactly which object is located. Breakline 128 is kind of our overfill protection, so we want to edit it. The editor offers us all existing configurations, and we choose the one we created during the creation of the retention basins. Right next to the preview of the breaking edge, we can then enter a new height for this breakline and also a name. If we are satisfied with the change, we save it and go on with the next breakline. However, as we are lazy, we don't want to open the editor all the time, but we want a faster way to edit the breaklines. Thus, we are able to edit them directly on the map. We enable the objects caption, and all the objects now have labels attached to them. They can be expanded and offer a quick edit component. So we enter a new height here. However, the component won't enable the Save button, as we did not select the configuration we want to attach this change to. Thus, we open the configuration selection widget and select our previously created configuration. Now we are allowed to save our modification. We repeat the steps for our graben. Notice that the Save button is enabled as the selection in the configuration widget remains. Finally, we have done all the changes we want to implement to prevent the damage to the property in case of heavy rain. If we open the catalog again, we find all the changes we made in this configuration. To see if our modifications would really help, we start another simulation. We use our new configuration and the old rain event. We could start another simulation now, but as this will take a while, we have a look at the optimal simulation result, which implements all the changes that we just did. We see that there is nearly no water that damages the target property. Hence, we now know that this planning option would stand a good chance in case of a heavy rain event. In the previous part, we succeeded in protecting our target in case of a rain event that has been created of current data. However, to truly plan for the future, we must not use current data, we indeed have to use future data. This data can be acquired using the rainfall common service of the SMS. We simply have to let the service project our IDF data to a future point in time. We choose to do rainfall downscaling on our IDF curve. We select a scenario from the list of available rainfall downscaling scenarios. A short description is displayed below the list, and a more detailed description is opened in our default browser if we click on the description text. For our use case, we select the ECAM5 A21 scenario because it is the most pessimistic one from the list. After that, we are asked for a target year for our data. Finally, as always, we enter a name for the downscaling and send the package away. This downscaling process usually takes only a few minutes. We could do some further plannings until the downscaling is finished, but we'll simply wait now. When the run is finished, a dialog pops up to notify us and to ask if we want to download the results now. We choose yes, and after a few moments we are notified that everything is fine and that we may now see the results. Again, we choose yes and are presented the downscaled IDF curve. If we compare values, we see that it basically is going to rain more. In order to check our previous planning with the new values, we generate a new rain event from the future data, just as we did in the first place. After we have finished the wizard, we are presented the new rain event with future values. We initiate a new simulation, select our previous planning and use the new rain event. To speed up things, we prepared the results of these settings too. What we see is not very satisfying. Our plans may be okay for now, but in the future it is likely that they will not suffice to protect the building and we have to do another planning iteration to refine the modifications, and eventually we find a setting that suits the present and the future conditions. These 7 steps sum up the main use case of the WP6 pilot implemented in the Sudplan scenario management system. Thank you for your attention and goodbye.